In this video, we're going to prove statements with or and and. Okay, let's look at this first example. Let x be in R. Prove that x is less than or equal to its absolute value. Okay, so because absolute value depends on the input being a non-negative number or a negative number, we're going to do proof by cases. So proof by cases essentially means the following, that you have case 1 or case 2, or maybe there are some other cases, but just for the sake of this argument, just say you have two cases. So assume case 1 and case 2, you prove the conclusion. Okay, so this is roughly what you're trying to prove here, is that get the conclusion by looking at case 1 or case 2. Okay, so I'm gonna do the proof. Let x be a real number. Okay, then we're gonna consider two cases. Case 1, x is non-negative, which means that its absolute value is itself, right? And therefore, x is less than or equal to its absolute value, right? This inequality is true because it satisfies the equality part, right? Since x is equal to, or let me rather write it the following way, x is equal to its absolute value. We're done. Case 1 is fairly easy. Case 2. X is negative. Okay, since absolute value of x is always non-negative, we have the following inequalities. We have that x is less than 0. This is our second case, right? And 0 is less than or equal to absolute value of x, right? Because absolute value of x is always non-negative. Okay, so here we also have shown that x is less than or equal to absolute value of x. Okay, so from both cases, and this cover all possibilities for real numbers, because real numbers, remember, it has trichotomy, is either positive, 0, or negative, right? We group the positive and 0 into the first case, and this is the second case. So from both cases, which cover every possibility of x being a real number, we conclude that x is less than or equal to absolute value of x. Okay, and we're done. Let's take a look at this example. Let x be a real number. If x is greater or equal to 1, show that x squared is greater or equal to 1 and x cubed is greater or equal to 1. So we're proving the implication if P, then Q and R, right? So let's say that is P, this is Q, and this is R. We're essentially proving two things. Prove P implies Q and prove that P implies R. Okay. Proof. Let x be in R. Okay. And remember, we're proving implication, so we assume the hypothesis. This is what we want to show. Two things, right? Okay. Let x be in R and assume that x is greater or equal to 1. Okay, since x is greater or equal to 1, x is positive, and so x greater or equal to 1 implies that x squared is greater or equal to x, right? Because we can multiply this inequality with a positive number, namely x, right? And doesn't change the inequality sign. So you've got x times x, which is x squared, and x times 1, which is x, right? Okay. And so, what do we want to show? We want to show that x squared is greater or equal to 1. But you see that x squared is greater or equal to x is greater or equal to 1, so by transitivity, x squared is greater or equal to 1. Okay, now since x squared is greater or equal to x, and x is greater than 0, we have that x cubed is greater than equal to x squared, right? So we multiply this inequality, right, with x, and you get x cubed greater or equal to x squared. Okay, so again, we already have that x squared is greater than 1. So again, by transitivity, x cubed is greater or equal to 1. Okay, so we have shown that after we assume x is greater or equal to 1, we show that x squared greater or equal to 1 and x cubed is greater or equal to 1, and we are done with the proof. Okay, now we're going to prove statements with OR by an example. Let x and y be real numbers. If x times y is 0, prove that x is equal to 0 or y is equal to 0. Okay, the way to prove a statement with OR is to do the following. So let's assume that this is P, this is Q, and this is R. So what we want to prove is P implies Q or R, right? So one way to think about it is the following. We assume P, we want to prove Q or R, right? Remember that Q or R is true if at least one of them is true, right? So if we force one to be false, let's say you force Q to be false, then it must be the case that R is true, right? For the Q or R to be true. Okay, so that's basically the idea, right? In fact, you can actually show that this statement, P implies Q or R, is equivalent to the following. P and not Q implies R. Okay, you can show that these two statements are equivalent. I'm not going to show it here. Let's leave it that for you as an exercise. Okay, so let's do the proof. So we're going to rewrite the assumption, and then we're going to assume that P is true and not Q is true. Okay, assume that P is true, x, y, 0, and Q is not true, x is not equal to 0. Okay, since x is not equal to 0, we can divide xy equals 0 by a non-zero number, and we get y equals 0. And we are done with the proof. Okay, so again, how do you prove P implies Q or R? Assume P and not Q, and then show that R holds. Okay, and that brings me to the end of this video, and I'll see you in the next video where we're going to prove statements with quantifiers.